This is the 7th episode in a series covering the design and construction of a clock for my relay computer. In the last episode, I finally resolved the problems I was having with contact bounce, and arrived at a set of resistor and capacitor values that achieved my target timing. Here's a quick recap of where I've got to so far in this series. I've set out the basic design for a relay ring counter which can produce my clock signal. I was then able to simplify it, so that although the functionality is the same, it now only uses one relay per stage rather than two. This simplifies the circuit, but also eliminates some of the contact bounce I was seeing when using two relays in parallel. As I'm looking to target a clock speed of 6 Hz, I work backwards to deduce that each relay in the counter needs to be held on for 83 milliseconds, and through a bit of calculation, plus trial and error, I arrived at the appropriate values for the RC network that forms the heart of each ring counter stage. In this case, a 220 ohm resistor and a 47 microfarad capacitor will give me a delay time of around 76 milliseconds, meaning each stage will be on for 152 milliseconds, giving a clock signal somewhere in the region of 6.5 Hz. A little quicker than the target 6 Hz, but certainly good enough for my purposes. I'm happy the ring counter stage circuit shown here does what it needs to, so it's now time to build a prototype circuit for the full ring counter to see if everything works together. To do this, I'm going to use one of my breadboards, which makes this sort of thing nice and easy. Let's get cracking. Right, so here's the starting point for the breadboard, and I've already put some of the components in because, well, you don't need to see all that going on. So coming down here, you can see basically we're ready for each of the 4 relay stages. So we've got the RC timer made up here. So let's go above there. There you go. So you can see that you have the capacitor there and the resistor there, and then here you have your Zener diode and your regular diode back to back, and that's what's forming the protection over each of the relay coils. So here we can see the relay coil going off, so on the black and white lines. So the white line goes into the positive side of the coil and the black one goes into the negative side. So you can see there's 4 of those coming over to the board and 4 repeat circuits here, here, here and here. Just around the back as well, you can also see then there's a quick jump off to the negative line there just from the negative side of the coil coming in. As for the switch contacts, you can see each one of these you've got 2 sets of 3 switches, so over here and there. And you can see they just go off to the switch sets here. So for each one of these, let me get something that's a bit easier to point with. For each one of these, this side will be the normally closed contact. That's the common one, and that's the normally open. And again, normally closed, common, open. There's a little diagram just down here just to show you how that's actually looking. So also we've got the power line just coming in over here. This is on the usual test board that I've got together, and then these crocodile clips go off, snaking up here and off up to where the power supply is, all the way up there, and that's set to the usual 12 volts. Cool, right, okay, so let's start wiring the circuit out, and yeah. Right, okay, then let's start with the voltage inputs, which are here, here, here and here. These are just going to go to the common side of the first switch set on each relay. Okay, there we go. Right, and then let's join up each of the contacts to the next contact in series, which then goes off back to the relay coils here, here, here and here. Now if I've got all the wires in the right place, if I put the power on now, I should get some clicking. That's a good sign. Alright, let's wire up a few more bits. So it'd be good to be able to see the intermediate stages on this, so see when each of the relays is active. So let's wire up the points A, B, C and D, shown here. And what I'll do is I'll take a point off here and just bring it down to this block of LEDs here. So same for this one. And let's see how that looks. Good, looking good. Okay, now finally then, let's just wire out this clock line. So again, this is where, if you look at the graph here, we want it when A and D are high, or B and C are high. And that's done with the crossover just here. So let's put that in now. So we're going to take from this switch here, we're going to take the, where are we, number 3 here, yeah. So voltage coming in here. Oh, it's going to be a bit of a tight fit. Let's move this just back a little bit to behind these things here. Better. So the normally closed side of this switch goes to the normally opened side on that one, like that. And the normally open side goes to the normally closed side, like that. And then I should be able to take a tap off just here, and that can be the clock signal going there. So now if I try powering on now, hopefully these should sort of do a little light chaser, and this one should be flashing on and off. Oh, that's looking pretty good. Okay, so I think what I'll do now is I'll just quickly do a slow motion shot just of this here, just to so you can actually see what's going on. But really the best thing to do now will be to take off a tap here and run it through the scope on the computer just to see what the clock signal is actually looking like. Okay, so we've got the scope set up again, and again, if we're just looking over here, I've got the blue line coming in just straight off the clock, and then I've just got the ground just coming in back off the ground rail at the back, somewhere near at least to where the other side of that relay contact is. Looking at the screen here then, so I've set the trigger for 6 volts rising, so that's where the middle point will be. And I'm going to set this to auto and just see what it looks like. So alright, well let's just get on with it. Let's switch the power on and start recording. And there we go, we can see the clock signal coming through. Now let's just pause there and turn the clock back off again. So let's see what we've got here. So I've set this to 100 milliseconds per division, which gives me basically a second over this entire window. And if we count the peaks, we've got 1, 2, 3, 4, 5, 6. That's obviously the starting of the first one again. So that's 6 peaks and troughs over the time, so that's my 6 Hertz. Now let's have a look at some of the timing of these. So if I just refer back to my chart, just get my iPad open. So I'm expecting, timing wise, and I'll bring this up on screen for you guys. So I'm looking for about 167 milliseconds over these peaks. From the peak to the next peak. So peak to peak should be about 160 milliseconds, 167 milliseconds, and actually it's 146. So again, it's in the right sort of ballpark. And actually looking on my screen, I think we did say it was going to be somewhere around that. Cool, okay. So that one is 146, but looking back here, this one's 178. So they're quite uneven. And yeah, you can see actually here there's a bit of a pattern where you have sort of a wide gap and then a narrow gap and then a wide gap and then a narrow gap. And I think I know what that probably will be, and that'll just be some of the tolerances in some of these components. So again, as I mentioned before, these capacitors can vary wildly. So what might be worth me quickly doing now, just see if I can get this evened up a little bit, is to just get out the multimeter and just test some of these capacitors and try and find 4 that are well matched. And same for the resistors as well. If I can find 4 resistors that are quite well matched, that should give me the best shot of getting a consistent timing. All right, well let's try that now. Okay then, so I've got my setup here, ready to go. So I'm just going to try each of the capacitors in turn and just see what value they are. So to do that, I've got my little multimeter here, and I've got 10 of these, so I'll do each one in turn. So for example, if I first of all hook up this one, again, just got to be careful not to let the leads touch each other. Okay, that'll do, and try that one. That's 40.5. So you can go there, and you're 40.5. And let's try the next one. Certainly a fiddly job. I'm going to do it to the nearest 0.5 because I think that should be enough precision. Let's try another one. Faulty dead. Do need to get that power supply. Do need to get a new battery for this as well at some point. Oh, right, okay, I'm going to do this in real time, but why don't you go into high speed mode now for the rest of this. Right, okay, there we go. So looking at these, it looks like 40 is around the best value. So I've got a 40 there, and I've got a 40 there. And then what we got close, I've got a 40.5 there, so we'll take that. And then the next nearest one, it's probably the 41, I think. Yeah, that one. It's interesting, some of these. So you can see this one here is like way, way, way out. And then we've got a couple that are quite high here. But that's good. So we'll take that one. We'll take that one, and that one. And the rest can go back in the bag for the moment. Alright, well, let's see what that does to the timing. Okay then, so back at the scope again. Let's give this a try. Okay, so let's see what difference it's made. Not very much at all, actually. So let's see, 166 that way, 143 that way. Not too bad. See, actually, what I might be able to do here as well is just try switching the caps around a little bit as well. Just see if that makes a difference. Could also be the resistors as well that are down. And the whole point with this clock is as well, it's never going to be a perfectly perfect clock. Let's just see what this does. Okay, let's just switch this one for this one. I haven't actually tried the resistors yet as well. They could be the wrong values, but I think after this we'll probably just finish there because you get the general idea. $204, 172. That's not too bad. And again, we've still got the 1, 2, 3, 4, 5, just over 6.5 Hertz there. So actually what I should be able to do with this as well is add in a measurement. So if I measure, let's have a look, frequency. See what it says. There we go, so we're getting about 6.3 Hertz on average. If I bring in the duty cycle, we can see what that looks like as well. There we go, not too bad actually. You know, again, for a clock made of resistors and capacitors, I'm pretty pleased with that. Okay, I think we'll stop there for today. Right, so in the next video, I need to add a bit more functionality to this clock, because at the moment you can see I can turn it on and off with power, but actually I need to have a bit more control over it. So I want to be able to stop and start the clock, but I also want to be able to freeze it as well. So basically I want to add a command to the computer which will allow you to pause the clock at the end of a program. And maybe ring a bell or something like that. So let's look at that design in the next episode. But for now, that's it. Thank you very much for watching.